Hi, the topic is on introduction to nanotechnology, and objective is just ice breaking before going into a detailed discussion on this area. So I will suggest you guys, if possible, could read or skim through this Engines of Creation 2.0, the coming era of nanotechnology by Rick Dexter. So, what is it? What is nano? What is this about? So how do we define it? So on the slides, we are exploring the scale of nanotechnology upon various scales, and this deals with materials and devices. So basically, uh, just forget about this diagram for a minute. How do we define it? So we have a materials and devices having functional features within a length scale between 1/10 and several hundreds of nanometers in 0, 1, 2, or 3 dimensions. So basically, we are restricting electrons or uh, free electrons. For example, if you take metal and nanomaterials, if you restrict in 0th, 1th, 2, and 3 dimensions, any one of these dimensions should be restricted to a nanometer scale. Then we can call this as a nanomaterial or engineered nanomaterials. So as you can see on this left hand side, you can see the topmost there is a water molecule, and the bottom we have a baseball. So basically we have a very small molecular example and a larger example, that is a baseball. It can also kept a human. So it's just a comparative. So you can see nanoscale is like very small. In it also occur naturally. Hemoglobin molecule, DNA is in nanoscale, viruses, and some bacteria are in nanoscales. Okay. And there are two ways we can go about making this nanomaterial to keep this thing in short. Uh, Either you can go uh, top down and bottom up. And top down is like you're taking a larger particles and you're breaking it down to reach a certain length that is desired, or a certain window that qualifies as a nanomaterial. Similarly, if you start from a smaller molecule such as a gold atom, and you start building it by chemical reduction or any other chemical method or physical method, you start building it and you created a lattice, a layer by layer, or any other means we'll discuss it later. So that process is called uh, bottom up. So you're uh, creating something out of much smaller particles. Means you start with the atom, you go to a cluster, then you go to a nanomaterial. So that's a bottom up from top down. So these are two paths where we can make or engineer a nanomaterial, right? So just a moment. Right. Okay. So these are some examples. These are liposomes. Fullerene is a carbon-based material, and dendrimer is a polymeric. Dendrimer is very interesting, and you can control each and every aspects of it from a synthetic path. It's a polymeric material, and we have a carbon nanotube and a graphene. This is just representing some kind of single walled. There are multi-walled. One end is closed, and two end can be closed, and two end can be opened. chemical methods, and this is just graphene. And you can get, if you want some functional groups here, you'll find it mostly in reduced graphene oxide, carboxylated. For example, even in carbon nanotube, if you want to make it suspended in aqueous media, you have to add some functional groups to it so that it will interact with the aqueous media. Otherwise, it will stay hydrophobic. And so to define it, materials in devices having functional features with a length scale between 1/10 and several hundreds of nanometer in 1, 2, or 3 dimensions. 0, I just added it, so just to represent a quantum dot. But it might, okay. So 1/10 of a nanometer is the diameter of hydrogen, so 1 angstrom, that is. Thus, this technology does not deal with subatomic particles. So we are not going below atomic scale. So we're not dealing with subatomic particles in this technology, right? So this means we are working at extremely small scales, but still not at the level of subatomic particles. So on this slide, we categorize various sources of nanomaterial. First, we have naturally occurring examples such as volcanic ash, bacteria and viruses. Bacteria are uh, natural, you can say, a nanorobot, and viruses and mineral composites. They can be found in mostly, for example, I'm talking about bacteria now. Bacteria usually you can find it very small and like 700 nanometer, 800 nanometer diameter. You can find it. Means it's restricted in uh, one dimension. I think it's restricted in 2 dimensions. So in one dimension does not have any restriction. So it depends upon the type of nanomaterial and type of bacteria. If it is staph, spherical. If it is bacillus, a cylindrical bacterium. So it depends on the type of bacteria. And viruses and mineral composites, not all viruses. Some viruses are very large. And mineral composites, these materials form in nature without human intervention. Means these are naturally occurring nanomaterials. Next is incidental, means unaware we were making them. So like utility smokes, diesel exhaust. So think of utility smokes, diesel exhaust, welding fumes, and industrial effluents. Although these are not intentionally produced for their nanoscale properties, they still have significant impacts. Lastly, this is what we're talking about, and this will be spoken in later stages too. It's like this is actually engineered nanomaterials. This is what we call engineered because we are aware and we are creating, controlling the synthesis and all the parts. So lastly, we see engineered nanomaterials. These are deliberately designed and manufactured for specific application. Example include quantum dots, colloids, buckyballs, buckyballs, carbon nanotube, and among others. So this is an representative image of a quantum dot. You can see there is varying degree of color. It can be actually controlled by controlling something they call band engineering that we can discuss later. So this is it's a representative image of a colloidal nanoparticle, colloids, and that's it. So this variety shows the extensive range of nanomaterials and how both nature and human activity contribute to this field, right? Some of the things that is not discussed here is like the Catholic paintings, some of the ancient cups that uses nanomaterials, and also Faraday uh, when he used to try to slice thin slice of gold for his experiments. Uh, Unaware, he made a pinkish or a ruby red colored solution that turned out to be gold nanoparticles, and it's still preserved in Royal Society of Chemists Society, I believe, at London. Uh, Here we'll discuss why. So nanotechnology emerged. So you can see nanotechnology, like a lot of people are talking about that, and you will get arguments sometime like, is it even real or everywhere? So is it actually real? So nanotechnology emerged in 1900 to bridge gap between different scientific disciplines. The idea was to stimulate interdisciplinary cooperation to encourage experts from varied fields to work together at the nanoscale. This convergence has led to a diverse range of subdomains within nanotechnology. Means you can fit nanotechnology in any domain. Additionally, global investment underscore the importance and potential of this field. For example, between 2005 and 2009, the US invested about $1.4 billion per year, while Japan invested around $730 million per year. Between 2005 and 2008, Germany, France, and Korea also made significant contributions, with investment ranging from 280 to $500 million annually over various periods. These figures reflect a broad commitment to advancing nanotechnology worldwide. Applications, let's come into that. As we were talking about investment. What came out of it is nanotechnology has a transformative impact across multiple sectors. So let's see what sector it has. In the semiconductor industry, it underpins the miniaturization and enhanced performance of essential components like CPU, RAM, and storage, and transistors. You can see Moore's law. The transistor is predicted to get smaller and smaller and increasing computational power. And organic light emitting diodes, which could enable flexible display, and quantum computers, uh, for which the base uh, Blaze platform, where this quantum simulation, quantum operation, computing done, uses techniques such as nanotechnology, nanomaterials to control the qubits. So in energy sectors, let's move into energy sectors. In the energy sector, nanotech innovations are pivotal in advancing battery technology, improving fuel cell efficiency, and boosting the performance of solar cells. The fuel cell is still an exciting topic, and right. So crucial steps towards sustainable energy solutions, and material science also benefit greatly too. Such as nanotechnology enable the creation of advanced materials such as ultralight aerogel, nanotubes, incredibly strong nanotubes. So it can be manipulated, and because it has multi-volt uh, capability, you can use it sort of like a muscle. The highly reactive nanoparticle means uh, I will discuss it, but just to say it, it has higher surface area when we go small, and things will behave differently. So we have highly reactive nanoparticles, which could be catalytic uh, and could have various surface applications, uh, all of which provide enhanced mechanical, electrical, and thermal properties. In life sciences, nanoscale approaches revolutionize healthcare. They allow for targeted drug delivery systems, such as mostly used for cancer, because the drugs are active ingredients of the cancer drug is quite toxic to a normal cells too. So, if you want to target poison to a particular area of interest, then you can use this. And scaffolds, that is development of biocompatible scaffolds and innovative techniques for tissue regeneration. These advancements are setting stage for breakthrough in diagnostic, therapeutics, and regenerative medicines too. So, but there is a catch here. So you cannot use in terms of medicine and drug delivery everywhere nano, because when there is a need, then you can use it. We cannot control everything using biologics, because most of the things can be can be done through biologics, but they might have limitations. Either they could be metabolized, or we'll discuss that in later. They could be metabolized, or they could be degraded by the in vivo environment. So these complications could be solved by using other technologies such as nanotechnology. This is one of them. Next is nanotechnology empowers us with techniques to engineer unique materials tailored to specific needs. These materials are designed to deliver superior strength, lightness, cost effectivity, durability, precise applications. In applications, basically, what we're trying to say here is that in olden days, if you want to, for example, you have a steel, say you have some material which, for example, the manufacturer, the customer need a different property or different standard. So what we do is we store that material, we'll computations, for example, stimulate the material, we'll treat and we'll do hit and trial or hit and trial, not so much, but educated guess or educated and informed decision and design we will do to make a new material, such as modifying alloy ratio or composite values. So to get a new material, and then it has to be fit to a industrial supply chain or manufacturing pipeline. Then you'll get a new material, then it'll be manufactured, then it will be uh, handled or it will reach the consumers. So you can see that obviously there could be a cost in it, right? Nanotechnology offers that using the same material that you throw out, uh, what do you call using the same material, instead of throwing it out, you just take the same material and you manipulate the material property, like manipulate the dimension, by changing the dimension, porosity, or I introducing certain impurity. The lattice could could alter the property of the same material. Instead of searching for a new or novel material, you can just understand some concept of nanotechnology and manipulate the same material in such a way that it will give the strength or uh, durability that you desire, right? So that's why what we mean by that serve our needs of strength, lightness, cost effectivity, durability, and precise in application. Also, you can find in some of the consumer goods such as paints and cosmetics that we use. Cosmetics we use nano zinc oxide, titanium dioxide does for yeah, such as titanium dioxide, zinc oxide. Some of the biocompatible is being used, and in paints it is used also. And this is actually conductive paint. What you see here, it's used for printing via inkjet or screen printing to get conductive electrodes or PCBs. So there are concerns rather than limits. So while nanotechnology holds incredible uh, it's crucial to address safety concerns for both health and the environment. Some nanomaterials may pose risk if not managed correctly. We must ensure that these innovations do not replicate, be sure not to create a new plastic pollution, so called. We must ensure that these innovations don't replicate issues like plastic pollution. So, yearly intervention and thoughtful regulations are essential to mitigate potential hazards and promote sustainable development in this exciting field. So, concern is there for safety, both health and the environment. For example, you create a nanomaterial in your laboratory, and how do you discard it? So, because the property or the effect of this nanomaterial in the environment is not known, right? So how do we discard it? So to discard it, maybe you can make it just store this nanomaterial safely, and there are certain process we can use. For example, you can bring it back up to that speed, like make it into bulk or make it into a form that is that does not have a nano or the property that is achieved by the use of nanotechnology. Then it can be discarded by a standard procedure that is existing in the industry standards, right? So that could be one of the way, but there are proper ways, and we can look into that too. So, Eric Dexler is a well-known figure in the field of nanotechnology. All the beginners or just who are getting introduced to nanotechnology can read this book, Engines of Creation. So this will be could be a starting point for a lot of thought experiments for people starting out. So in this influential work, Dexter introduced the concept of molecular manufacturing, envisioning machine built at the nanoscale that could fundamentally change how we produce goods. So molecular manufacturing is sort of nanorobotics, and there is different take on it, and there are some progress, but not actually how it is mentioned in the book. So he discusses not only the technological possibility, but also ethical, societal, and environmental challenges that such advancement might bring. His ideas help to spark both excitement and caution in the scientific community, laying the groundwork for ongoing debates about the benefits and risks of the nanotechnology. So, for anyone interested, just tap into this and look at Dexter's work. So, it could be a pivotal, vital point for reference for potential students in this area. That's it. Thank you and have a nice day.